You know, deep inside massive industrial plants all over the world, there are these machines that are literally the beating heart of the whole operation. Today, we're diving deep into one of them, the centrifugal compressor. This thing is an absolute powerhouse that makes everything from your fuel to plastics possible, and we're going to break down exactly how it works its magic.
But let's start with a really basic question. If you've got a gas, how do you actually squeeze it? How do you add energy to it to seriously ramp up its pressure? It's not as simple as just, pushing on it. This is the core problem that leads us straight to this incredible machine.
So here's the game plan for this explainer. First up, we'll meet the machine itself. Then we'll get into the really cool part, how it turns pure speed into pressure. After that, we'll have to talk about the physics, the rules of real gas. Then we'll see how we measure its performance and explore the dangerous edges of its operating limits. And finally, we'll see how all this knowledge creates the absolute foundation for controlling these things.
All right, let's jump right in with Section 1, Meet the Compressor. Before we get lost in the weeds of physics, let's just get a really clear picture of what this machine is all about.
So what is this thing really? Well, at its core, it's a dynamic, spinning machine built for one job, to take a gas and dramatically increase its pressure. But here's the secret sauce. It doesn't use brute force. It uses an elegant two-step physics trick. It converts speed, or kinetic energy, into pressure, or potential energy.
And that right there highlights a huge difference in approach. See, a piston compressor, that's positive displacement. It traps a chunk of gas and physically squeezes it. But a centrifugal compressor is way more elegant. It works with a continuous, smooth flow of gas. It never traps it, it just manipulates its energy as it flies through.
Okay, so how does it actually pull off that incredible energy conversion? Well, that brings us right to Section 2, from speed to pressure. Let's peel back the casing and look at the brilliant mechanics at work inside.
Inside the compressor, you've basically got 3 stars of the show, and you can see their names here in both English and Farsi, which is a cool nod to how global this field of engineering really is. First, you have the impeller. It spins incredibly fast, and its only job is to grab the gas and sling it outwards, adding a ton of speed. Next up is the diffuser, which cleverly slows that fast-moving gas down. And finally, the volute, or the casing, which is shaped like a snail shell to collect all that newly pressurized gas and send it on its way.
So here it is, the whole journey in 3 steps. Think of the impeller like a crazy fast merry-go-round. The gas gets on in the middle, it gets flung to the outside edge at incredible velocity, and then, as it flies off into the diffuser, that sudden slowdown forces its kinetic energy to convert into potential energy. In other words, speed becomes pressure. It's that simple, and really that beautiful.
So we've seen the hardware, the mechanical parts, but honestly, that's only half the story. To really get a handle on this machine, you have to understand the stuff it's working with, the gas itself. So, welcome to Section 3, where we have to talk physics, the rules of real gas.
Now, you might remember the ideal gas law from high school physics class. Well, I've got some news for you. In the high-pressure, high-temperature world of industrial compressors, there is no such thing. Ideal gas is a myth. We deal with real gas, which behaves, let's just say, it's a bit more complicated.
And the key to dealing with that complexity is something called the compressibility factor, or just Z. The best way to think about Z is as our reality check. It's this crucial correction number that tells us exactly how much a real gas is deviating from that simple ideal model. And trust me, without Z, our calculations wouldn't just be a little off, they'd be dangerously wrong.
And there it is, the equation that governs everything inside that machine. It looks a lot like the ideal gas law, you might remember, but with our little reality check, Z, plugged right in there. This formula, connecting pressure, volume, and temperature for a real gas, is the mathematical bedrock that all compressor control systems are built on. Okay, now that we've got the physics down, we can move from theory to practice. It's time for Section 4, Measuring Performance. Because in engineering, there's a golden rule. If you can't measure it, you sure can't control it. So let's look at the vital signs that tell us how the compressor is really doing.
Think of these as the compressor's vital signs. It's the language it speaks. We measure the mass flow rate. That's how much gas is actually moving through it. We watch the pressure going in, the suction pressure, and the pressure coming out, the discharge pressure. A really key number is the ratio between those two. We also track something called head, which is just a way of saying how much energy or lift the compressor is giving to every kilogram of gas. And of course, the big one, overall efficiency. How well is it turning electricity into pressure?
And this really just sums it all up. These numbers aren't just random data points on a screen. They are the language of the compressor. They tell us exactly what it's doing, how hard it's working, and most importantly, if it's healthy. Every single control decision is based on reading this language perfectly.
All right, Section 5, Operating on the Edge. Here's a critical point. A compressor can't just run at any random flow or pressure you want. No, it has a very specific map of where it's safe and stable to operate. And if you stray outside those lines, well, things can get catastrophic fast. So you have to know the two big danger zones. On the low flow side of the map, you have something called surge. This isn't just a little hiccup, it's a violent flow reversal, where high-pressure gas downstream literally slams backward through the machine. It can sound like a cannon going off and can tear the compressor apart. On the other end of the map, you have choke. That's the machine's absolute top speed. It physically cannot push any more gas through. The whole game is keeping our current operating point, where we are right now, safely in the zone between those two cliffs.
And that is the entire game. The whole incredibly complex, often multi-million-dollar control system built for one of these machines has one primary job: keep the machine out of surge and away from choke. It's all about managing that operating point and staying within the safe envelope always.
And that brings us to our final section, where we tie it all together, the foundation of control. Let's talk about why understanding all these first principles isn't just academic, it's absolutely everything.
So, why did we go through all of this? Because you simply can't do the practical stuff without the theory. Understanding the physics of the gas is what lets engineers design the right pipes. Knowing the internal components is how they choose the right motor. And grasping that performance map we just talked about, that is the only way to design a control system that can prevent a catastrophic surge. This knowledge isn't just helpful, it's the non-negotiable bedrock.
So in the end, we see this machine as governed by strict rules of physics. It has its map, it has its boundaries, it has its hard limits. The ultimate challenge isn't just building the machine, it's deeply understanding its language, the physics, the metrics, the operational edges. Because true control doesn't come from fighting the machine, it comes from mastering the rules that govern it. And that mastery is what keeps these powerful engines of industry running safely and efficiently. Every single second